All right, folks, this is a video that's a continuation about torque. This is about center of gravity and net torque. So center of gravity is worth talking about because we are going to talk a lot about the torque due to gravity. And so we have learned about center of mass. Center of gravity is technically a distinct topic, although in this course they are the same. Center of gravity is the point at which an object's weight is considered to act when calculating torque due to gravity. For objects that are smaller than, let's say, an ocean liner or a skyscraper, the center of gravity and the center of mass are in the same place. So the first thing that we're going to assume is that the location of the center of gravity is the center of mass. Now, this is a facet of AP Physics 1 and most introductory physics courses. When objects are very, very large and their mass is not distributed evenly, their center of gravity can be at a different location because the ends of the object are very different distances away from Earth's surface, let's say, or Earth's center. So that's the first assumption. The second assumption I want you to make is in this course, it's going to be at the center of an object. When you're considering rotation, the center of gravity is going to be at the exact center of that object. You need to pay attention to whether the center of the object is where the balance point is, but it's going to be at the center of the object. So here's an example. If I were to put a block on the floor like this and the ground was flat, the center of gravity would be right in the middle. That is the point at which gravity acts. Now, the axis of rotation is going to be around the bottom of this, right? If the thing's going to fall, it's going to be around the bottom, and so the torque due to gravity is going to be 0. However, if I put this block on a slanted surface, now the value of r and the value of the force of gravity are not collinear. They're not along the same line. And so the torque due to gravity is not 0. Now there's an angle between those two vectors, and so there is going to be a torque. All right. So I wanted to explore torque due to gravity and then net torque in this video. So first we have a sign, and we're going to draw some forces for that sign. When you're drawing a free body diagram or a force diagram for a big object, that rotation is important. You want to draw it as it's actually shaped. You don't want to draw it as a dot because the forces are happening in very different locations. So there are chains supporting this physics sign. There's a chain on the left that's going to be pulling up. I'm going to call that TL, or the tension along the left chain. And there's a chain on the right. I'm going to call that TR, for the tension along the chain on the right. Because this sign has a mass, there needs to be a force of gravity. And so that's going to be Fg at the exact center. Okay, so that's an example where the force of gravity is in the exact center of the picture. That sign is not going to rotate because the two tensions are going to balance one another out. All right, for this balance board that has two people on it and they're standing on a fulcrum, you'll notice that the part of this beam that is to the right of the fulcrum is longer than the part that's at the left. So this diagram is more complicated. So we'll start with this bigger person over here. The bigger person is like way over on the side, and they have a force of gravity that we're going to call mg, big mg. So they're going to like push down on the board with their own weight. There's a little person at the far right-hand edge. Their force of gravity mg is going to be directed down onto the board. Then there's the fulcrum. The fulcrum's like a little left of center. The fulcrum's underneath the board, so it's going to push up. I'm going to call it F triangle for the force of the fulcrum. And then I do have to locate, like, at the center of this object, the force of gravity on the object itself. So this is different from the beginning forces unit, because we have to consider not only the weights of the people on the board, we have to consider the weight of the board itself and where that weight acts. All right. Now, to do any more analysis, we're going to have to identify an axis. So I'm going to go in a different color. I'm going to say, well, let's make the very center of this board the axis. And then I think it makes a lot of sense to make the fulcrum in this picture the axis. And that's going to do some very important things for us. So now we're going to calculate net torque. Net torque is the sum of all torques acting on an object for a given axis. Sometimes you get to choose the axis yourself. Sometimes it's obvious where the axis is. But either way, that axis must be identified. Now, there's ways to identify it without actually stating it, but I would advise that you identify the axis in some word. So we're going to do the net torque for the physics sign. We're going to find the net torque, that's sigma tau, at the center. So that's where like I've identified the axis. So on a diagram, it would be good to identify the axis. You can do it in words as well. The net torque is the sum of all torques. So I have to now look at this picture and decide whether the torques are going to be the same sign or opposite signs. Now this sign is not rotating. So I have to imagine like which way could each of these tensions rotate the sign about that axis. Well, I can imagine that there's R's that are those lengths, and I can imagine that if this tension were the only tension, then it would cause counterclockwise rotation. So this tension is going to be my positive tension, right? If someone's actually pulling on this chain up, the sign would rotate like this. That's counterclockwise. Whereas the tension on the left, that's going to result in clockwise rotation. That's going to be my negative torque. Again, if someone pulled up on this left chain, the sign would rotate in the opposite direction. It would rotate clockwise. So taking that into account, my net torque is going to be the torque due to the right chain minus the torque due to the left chain. You'll notice that I did not include the force of gravity. Maybe you can think of the reason why before I tell you. We would not include the torque due to the force of gravity because it's zero. Because it acts through the center, sorry, not the center, right, through the axis. Okay, if a force acts in the same line where the axis appears, then it can produce no torque. And that's really important for analyzing torques. Things get very complicated if some torques are not zero. All right, so let's do the balance board as our other example. We're going to do the balance board's net torque at the fulcrum. Okay, so it's like a seesaw. It's not the same length on both sides. And again, I need to decide what's positive and what's negative. Now, this big person's weight on the left-hand side, if I continue this around the axis, that's going to give me counterclockwise torque. The weight of the board and the weight of the small person, those, if I continue those around the axis, those are clockwise torques, and so those are going to be negative. So my net torque at the fulcrum is going to be the torque due to the big person's weight minus the torque due to the little person's weight minus the torque due to, we'll call that the beam itself. And so writing out expressions for net torque, the important things are to identify where the axis is, and then also to identify which torques would be positive, negative, or zero.